take a minute to pause the video to read the question in its entirety. What this problem is asking us to do is solve an application involving Newton's law of cooling. Now, down below, I have a screenshot here of Newton's law of cooling from page 362 of the e-text. However, I'm going to actually get a little creative here with this particular problem and go about it through transformations instead of the more formal algebraic methods that are presented in the text. So we see that the pizza is removed at 3 o'clock from an oven. It's 400 degrees. The room temperature is 74, and after 5 minutes, the pizza has cooled to 300 degrees. Now, I'm going to treat 3 p.m. as time zero, or an initial value. And I'm going to treat 5 minutes later then as time 5. So what I'm going to do here is put these 2 points, time 0, 400, time 5, 300, into a calculator and run an exponential regression. And I've already started some of that process here on this Desmos file. Okay, so you see those points, you see my exponential regression, and you see it's a perfect fit. Of course, it's only 2 points, but there's a problem. So yes, this model goes through the 2 points, but notice in the long run, it has a limit of a temperature of 0. In our problem, we were told that the room has a constant 74 degrees, or is a constant 74 degrees. So we would not expect the temperature of the pizza to keep decreasing past 74. In other words, this is going to be treated like an asymptote for this exponential decay. So how do I get around that? Well, I could transform my points by subtracting 74 from each. And now I have a new exponential model. Notice it's just been shifted down. And then I could rewrite that model here as y equals ab raised to the x. Okay, now notice it's in blue, plus 74. So in this way, it shifts up my exponential regression 74 units to account for the constant temperature in the room. Again, this is a little bit creative way of dealing with that constant room temperature, specifically in Newton's law of cooling type problems. Okay, now that I have this model, I can answer other questions. So I'm going to turn off this particular model, and I'll even turn off, I'll turn off those points. This is the model that I want to focus on. Okay, so if I come back to the questions being asked, the first one is the temperature of the pan is 135 degrees at what time? Well, I could come back over here to Desmos and type in 135, or y equals, hang on, 135. And now I can see there's a point of intersection between the model and 135 degrees. That happens after 22.9 minutes, or about 23 minutes, rounded to the nearest minute. So back to my question, where it says at what time, I would just need to tack that onto, that 23 minutes onto 3 p.m. So that's why you see here time 3:23 p.m. I can do something similar for part B. It's asking for how long does it take before the time, or before the temperature is 170. So notice I've just updated that to 170. I can click at that point of intersection, and it takes 17 minutes. You see I've put here 17 minutes before the pizza reaches 170 degrees. And what do you notice about the temperature as the time passes? You should notice the temperature of the pan is approaching 74 degrees Fahrenheit. It should not go below that. And actually, The way I approached this problem hinged on this fact because that's why we did the transformations to begin with.